Hey guys, can you see my screen now?
Yeah.
Yeah, so thank you guys. So yeah, this is the data connectivity solutions for robotics and vision systems. I'll just go over a few stuff like this is the Perseverance mission in the Mars. Like you can see the Land Rover or the helicopter over there, everything has a vision system. And if you have a vision system, you need to have a telemetry, like somewhere you need to record the data and process. So yeah, that is the brain and eyes of it. And it's not just the reason I took Perseverance is like the extreme conditions and the applications. So for example, we have firefighting drones. For agriculture, they would be spraying fertilizers, very toxic chemicals like phosphorus that could affect your design, material selection, and in mining, like constant dust pollution and everything. So this is the thermal imaging system. So this is where you need data connectivity, like you need 1 gigabits or 100 MB, depends on your application and the environment. So just to give you a feel of where we are heading towards. And also a few more challenging environments would be like underwater drones, firefighting robots at very high temperatures, and ROV. Even we do stuff for ROV, that is remotely operated vehicles. So they send it for oil and gas to, switch on the valve or turn off the valve, installation purpose. So we also do the stuff for the data connectivity and the mechanical hardware. So if you go underwater, you need to have metallic casings to, to withstand a very high hydrostatic pressure. So things start changing. So more and more deeper in the water you go, more bulky it gets. Whereas in the previous one, if you see these are lightweight, but the material selection and designs are very important. So these are the bunch of startups. I just saw it in the Google images for different navigation, military, insurance, entertainment, so delivery like FedEx stuff. You can use drone and vision systems for everything. For everything, you need vision system. That means you need data connectivity. So that's it. So we'll start jumping into the mechanical design of this. So for what are we designing? So if any of you guys starting to design, you need to ask for whom or which application environment is going to be like. So just to say like, let's design for your environment and application. Let's say we have an ambient conditions. So you start looking at these factors, like what is the temperature range? What is the shock? Is there going to be vibration? What is the flammability? All these factors come into picture. So what's your application? That would be the question. Like someone says, hey, I'm going to put the camera on a vehicle. Is it on road or off road? So if it's on road, it could be minus 40 to 125. That means it could be in Arizona. It can also be in Michigan when it gets minus 40 sometimes. And what is the shock when you hit a road and pit? Yeah, so if you go into a pit very often in Michigan, you're going to have shock. So the camera still has to function. It should not be disintegrated. And what is the vibration? So we put accelerometers. Um, so if you want to know what is your random vibration, it's very simple. Like just put an accelerometer in your car or which location you want to do it. It's like say in your dash cam or something, record it. So you'll just get a graph and that would be the random vibration. And 10 or 20 GRMS, it's like a root mean square, like average G force it's going to have is like say, let's say 10 G. So you got to design. And if there is a resonant frequency, the camera would come off or the vision system would come off. Next interesting thing is flammability. I would come in the next chapter, next slide. And more important is also the pollution level. Like, so yeah, if it's gonna be inside your room, like 4 is the extreme, 1 to 4. If it's inside your room, you hardly have any pollution. If it's gonna be inside the dash, like dash cam or something, very less. But if it's outside the car, yeah, it could be 4 or extreme, like in mining situations or in firefighting situation, yeah, extreme pollution. So what it means for high pollution is like there could be conducting dust. So these dust or moisture could be the very high moisture that could enter your system if it's not properly sealed, and it could have shorting. It could short your system, so it could just burn off. So that's some of the factors you have to consider. And next would be the fluid exposure. So what kind of fluids it's going to be exposed? Say it's an ambient condition, the maximum you're going to pour is water or coffee on it. That's really not a deal. But if it's on-road vehicle, depends on is it near an engine or outside. Let's say it's outside, and right now in Michigan during the snow times you have salt all over, so we have to have a salt spray. Or if it's near the engine, diesel, gasoline, we have to immerse the parts in it and see if its part is swelling up. Some parts would start swelling if you immerse in certain fluids. And says another thing is like mining fluids or dirt exposure. Is there any visible damage? The part is starting to peel off. So material selection comes into place. And sealing, you might have seen this very often in IP53, IP67, the way these are the IP ratings from the DIN spec. So it's like IP67 is like immersing into water, 5 feet water, and the water for 30 minutes, water should not penetrate based on the application. And next is the RF. So what is your application? You just want to put some small camera in your drone that just need like 10 Mbps. Yeah. But if it's like on road, we need very high precision, low lag, and all other losses. Yeah, we have several specs for each application. You have to refer them. And what's the speed like? I'm just touching basics on it. Based on your speed, you have to design the system. Could get bigger or smaller. Then we have to redesign the mechanical stuff around it. So yeah, this is going to be a thermal imaging camera. LiDAR will be even higher speeds. 10 Gbps it can go, or it's just going to be an HD camera or ultra HD camera, 4K. What is your application and the speed? So we need to consider RF and mechanical at the same time. So this is some pictures of what I meant in the previous slide. So let's say like what is the shock or drop test? You can think of a drop test of your phone over here if you have it. So you just drop it from a height, and that's exactly what happens when it hits a shock. A shock wave just passes through the mechanical structure, and some electronics could come off. And that's what the drop test is all about. So we can have for different applications, you can see for on-road vehicles in your car, that'd be 30 G. Can even go much higher, but 30 G. For extreme harsh, like a tractor, if it hits a pit, it can go all the way up to 100 G. Your parts can just come off, your camera systems and everything. So we got to test. This is the in-lab testing. You can see a shaker table. So if you just put the shaker table and install these parts, you can keep vibrating and see if it lost continuity. Is there a mechanical failure, electrical failure? Those are the things. And random vibration, same table with a different profile you would be doing. Next is the flammability. So this is very critical. So when you choose a plastic or any material, like mainly plastic, we have to look at the flammability, because what it means is like self-extinguishing property, that when you put a fire to a plastic part, we want to see like if it within 30 seconds, it's going to self-extinguish. That's what the time over here says. Like within 30 seconds, it's going to extinguish, or take 60 seconds or 10 seconds. For example, you have an Amazon warehouse, you put your camera systems there to monitor, something happens and catches fire. You want it to extinguish itself by 30 seconds, not spreading the fire anywhere. If it spreads, all the goods will be burnt down. So those are like very high requirements even for a warehouse. You can imagine for a automotive or tractor, all these applications. So yeah, choose your material accordingly. If it's ambient condition, yeah, they're expensive stuff. They have some additives to get it. V0 means like fully self-extinguishable within 30 seconds. So that's what V0, V1. V1 is like 60 seconds. HP is like, yeah, let it burn till it goes off. So that's like ambient room conditions. So what's your application? You can start filling it out. And this is the fluid exposure. You can see we have some fluid like diesel, gasoline, or let's say like carbon fume, hydrant fluids in firefighting, and just immerse the part in it for 2-3 hours. Bring it out and see if the part was swelling or the material color has changed, color came off, what kind of damage it has gone through. And this is the sealing capability, IP67, that means ingress protection. The first digit is for solid particle protection, second is for liquid ingress protection. So when you say for like, yeah, if you say like IP53, it's like smaller dust. Let's say 53, smaller five. This number is for solid, so it's dust, and second is for liquid. So 3 is like spray, like something over here. This is like IP53, like rainwater drizzling. So IP54 is like heavy rainwater. IP67 is all your phones, Apple phones or any Android, it's IP67. You just drop into a bucket of water, you bring it out, dry them, it should still function. And IP6K, 9K is extreme. It's a high pressure spray. You just have a very high pressure spray hitting your part, still it has to function. So yeah, what's your application? And for here, it's like IP6K, 9K after the heat exposure. So very high heat exposed, and the plastics could even melt or come off, or they get loosened up, they expand, and now still they have to pass the testing. So we have such requirements for based on very harsh conditions. So these are the stuff when we start, even designing uh, the systems, we would start thinking, oh, where is it going to be? What are the things we have to consider? Do we just, this is kind of a mental framework we have, or just start putting it up and collecting the data based on which we have the material selection, like V0, V1. You can go into Google and find we have some chosen materials for manufacturable materials. And based on this, our design goes on and we start analyzing. So why should we do all this for the mechanical design, right? Just do something in a CAD model and just keep running around. Why should you do all this? So yeah, these are some of the failure modes that could happen. You can see this is a rover's wheel. Um, so you think it's going to be running on your carpet? No, it's going to be running on some road or like rough terrain like this. You just break off. What's the point? It's electrically function and everything came off. And these are some drones. Like it looks like there was a high temperature and just fumed off inside. Not sure what happened. So yeah, it could be exposed to very high dust, like in a mining application or something. Dust or moisture could have entered inside the system and shot it. That could have happened. Or just this one could be like in Arizona or something, very high heat, just hit the wall or shock. Maybe it wall something, it could not withstand a 10G or 30G shock and came off. So we need to understand the failure modes. So it's like a loop. What's the failure mode? Have we really addressed the pre-design? So that's how a good design engineer goes forward. So how do we approach this design challenge? So same thing again, coming back. I'll just take an example and show, but most probably like usually we will run some FE analysis like flammability and everything. Let's say temperature range, shock and random vibration. We'll run some analysis, see the stress strain. The software tool will use is Ansys. For flammability, it's pretty simple. We have the UL94 spec. We can see V0, V1, whatever you want based on your cost, you can choose. And the application. Pollution level, know your application. You can design accordingly, choose the right material. And fluid exposure, you saw the immersion testing, like putting in a test tube of all colorful liquids and seeing what's happening inside. And sealing capability again, what's your environment? And we can also do an Ansys seal testing and everything, but it's we call it hyperelastic FE and LS Dyna we use. But yeah, we can still do it in Ansys. And RF performance, what's your application? It's a LiDAR system, it's a camera system, and so what are the losses, lag, EMI shielding losses? You can use Ansys HFSS. So Ansys is like one-stop shop where they have all the tools on the planet to do anything you want. So yeah, let's see an example. So let's see, this is like a typical bracket for a camera system, right? So you can just take this bracket anywhere and install in any of your rover or the drone or anything you want, you can put it. So this is like let's say this back bracket system. So this blue one is the battery, and you can see it's a battery enclosure on the top, and this is where we just hold on to the, based on your skeletal framework for whichever application we'll just hold on. So we just divide a big system into subsystems. So let's call this subsystem as a camera system. So this is the primary battery enclosure. You hold the battery, that'll be quite heavy. And next would be this would be the action camera, like a GoPro. Looks like more like a GoPro. And next, this would be held on by another GoPro bracket, action camera bracket. That would be held on from another bracket. So it's a bunch of brackets held on. And this is the servo motor. So it just gets connected from here to your ECU, wherever that gives a signal to move up and down, or from your remote, however you want to move. So this is more mechanical. I didn't go into the electrical side. So we can see how this is quite bulky. This is all made of plastic. Let's see how it functions. And this is the servo tilt bracket. Based on the angle, the servo motor will be turning around. So this is the mechanical system. So I just gave some load sensor, like what would be happening. So based on this system, like what you're seeing is the failure mode. Like I just recreated a failure. Like there are some loads at the servo motor system. If there was a load on the servo motor, you can see the bracket would be failing right here. That is the case. Yeah, more failure happens, fatigue or anything could happen. And you can see this compared to blue is all zero. When you see red, that means there's a high load is happening right there. So that's how we start with we first make the design and we do an iterative process. So now we should increase the bracket design, like increasing the thickness of it to reduce the stress generation over here, or even change the material. We can also change the material to move away from the failure criteria. So these are some of the like very basic systems to do. Like you start with an FEA. Now you can also from here you can all the thermal loads and everything like static thermal analysis. You can do it, and you can start seeing everywhere the red portions and design it in such a way you already know what's the failure mode and you addressed it. And this is the vibration analysis. Did I run it? Okay. So let's say like this is the resonance frequency at 156 Hertz. Okay. So this is a simple modal analysis. That's all the vibration analysis starts with modal. From there we go for random vibration, shock and everything. So people who know about resonant frequencies, like, yeah, that is the natural frequency of the system. At this certain frequencies, there'll be like bunch of natural frequencies. They would start happily, even though it's static, they would start having a modal shape. So this is the modal shape, and you can see this entire part is swinging around the bracket. So as this is swinging around the bracket, you can see the battery enclosures. You're going to see some stresses over here. On the top, the entire over here, all the shift points are going to change. So based on which either you have to, if your system is going to have 156 Hertz because of your rover motor or something constantly vibrating 156, rest assured they're going to fail. So you have to design a system in such a way you move the resonance frequency of the overall system away from 156. Again, if you again attach this to few more parts, the natural frequency could even drop. So yeah, you just keep this on mind and keep tracking how the natural frequency is going down. So at the end of the system, when you put your part, even at natural frequency, can it withstand? So mechanically and electrically. So with this swinging action at 156 Hertz, even there could be electrical failures inside. So these are the things, very simple stuff with the material selection and some Ansys analysis you can do on this. So for us, some data connectivity connectors for harsh. So what all you saw right now, we all take into consideration and design our connectors for extreme harsh conditions. These are the Ethernet connectors. So all this, we have tested it for very extreme high vibration, shock testing, and flammability. These are material like even it'll self-extinguish if you put into just light them. So all these have been taken into consideration, and these are some of the products. This is the 100 Mbps product. You can use for your truck, automotive, all the applications, Ethernet. And this is a FACA connector system, pretty common, been there for years, and all the automotive chassis and everything, you can use it. These are unsealed systems. Whereas this one is pretty sealed, you can use even mining operations and everything. And few more high-speed data connector systems. Just the same applies. The MATAX, this is for like 10 Gbps connectors, very high, 6 gigahertz connectors and everything. For LiDAR, like if you see like 4 of them, that means there are 4 camera systems or LiDAR systems over here. We have the plug, headers, and everything. So all this would be going into your camera to feed back to your telemetric system. These are another MATAX connectors that could be used for extreme harsh. So the material selection, the seals we have here, they are for the IP6K, 9K after heat exposure. So they can withstand pretty heavy temperatures. That's why they get bulky. So yeah, that's it. Go flying. Any questions, guys?
So nice presentation. Thank you.
Thank you.
Actually, what you showed in the beginning, you showed the experimental. Yeah, let's go back. Let's say, yes, this one. So design for your environment. That's what we call the working condition. So you definitely you have some tables that already has the data. So when you design, you usually do the experimentation and testing after you finish the product. Is that correct?
So yeah, so what happens is like this is what happens. We get from like application engineers or product managers would say, hey, we need connectors for automotives, or we need connectors for drone systems or parking camera systems like this. So they would give a set of bunch of conditions like what is the sealing, fluid exposure, and now like you just make the part, you design the part, and you do testing. And we have a bigger table than this. Not this is something I made it up.
Mhm.
But we have a spec, a lot of specs. We have USCAR, DI, and each company has this thousands of spec. So they have like 30 to 40 tests. And if
Yeah,
we do not consider these things proactive, and each one would start failing, and each test would take like 3 months, it will be like endless, like 10 years to release a product. So beforehand, instead of designing and failing at the actual testing, we would do some prototypes or we do simulations, and we have a lot of equations and these kind of tables from the material suppliers and everything. So we quickly do a design. So two parts of it, we do a mechanical design
mhm.
and we do a Ansys analysis, make sure that it's good enough. And now we come to actual material. So we start building a tool and get all the material. Then we would do the real testing. It'd be like engineering evaluation,
Yeah,
prototype testing. And once it all passed, then we move into production, full level production testing. We still see some failures there.
yeah,
So
that's true.
yeah, so that is, so we want to reduce the frequency as much as possible in the production testing, because that delay would be years if you do it. So in engineering evaluation, we would do a bunch of these testings as you see here. So that's the idea. Yeah.
Yep, thank you.
Any other question or anything you want me to go through? I have answers open. I can just show if there's something you want to know.
Yeah, so I had a question. So when you're going through those testing and for the mechanical considerations, what's usually the first one you test? What's usually the go-to one that is a standard in a way?
So um, yeah, the most challenging in my case would be the sealing. We see it's very difficult for sealing. So especially when you just drop it into like think of a swimming pool. You just put your phone inside, bring it out, and again use it. Won't you be nervous? So that same nervousness comes. So all our camera systems, we have to put in 5 feet of water, example, and also high pressure spray after heat exposure. So we have to do a heat exposure, humidity exposure at 125 C. That's like boiling temperature, higher than boiling temperature of water. So all your PCBs, the solder contacts, the plastics would start expanding. They expand and contract at minus 40 degrees Celsius. So it's like a fatigue, thermal fatigue. So pretty much they get loosened up in the contacts And when you dunk it into water, some water could have gone inside and you failed it. So we have a lot of software tools, but still we are very nervous. So that's the first thing I would do. And next would be the fluid exposure. We give some, a lot of the parts start swelling. Each part like nylon would absorb some fluids. PBT, PVCs, each plastic has an affinity to some fluid. And if for example, we designed it for automotive inside your dash cam, that's where we designed it. Somebody gets excited and puts in a mining or a bulldozer application, some fluids, it can start absorbing and get fat and break down. So that's, yeah, first would be the sealing, next would be fluid exposure. And most probably shock and random, we do pretty good analysis. So we know how to combat them. But there are cases where in vibration, the part was broken into two pieces. It hits a resonance with a very high G, it would have broken. But this is rarely seen because we do a good job of beforehand. These are something very hard to predict with simulation. So little bit, there's a gray area of nervousness there. Yeah.
Thank you.
Um, yes. Anybody want something to?
Can we go? Yeah, I'm sorry. So, could we go through the answers in terms of, let's see, the vibration? When you do have this kind of brackets that you have this battery here, you have the brackets, you have other stuff. So, how do you combine all that and get through
Yeah.
the analysis?
Yeah, I can show you. Yeah, let me just show you how it was done. Let me reshare my screen. Yeah, can you guys see my screen?
Yes.
Yeah, so this is the Ansys suite. They pretty much bought everyone, something they created themselves, something they bought, some like so explicit is to be LS Dyna they bought and integrated with it. So let's say we need a modal analysis. So this would be like, let's say I'll put it over here. So it starts with modal, and from modal you can go to over here. Let me yeah, I have it here.
Hey,
So I have the
quick question. What's the program you're using here? The software,
Ansys.
Ansys. Okay.
Yeah. So
Nice.
these are the several suites we have. So we have something like modal, and so from the modal analysis, it starts feeding onto each one of them. So let's say from modal analysis, I can do random vibration, harmonic, shock, everything you can do. So let's go to modal analysis. Yeah. So yeah, you can just go ahead and assign the materials and everything. So here you can see this is the system, and yeah. So I'll show you how this system was defined before we go forward. Yeah. So this is the same camera system you saw. So the fixed support is the blue ones. So right here, I just given a fixed support, like you just put a M4 screw from bottom and just screw it up to your skeletal structure chassis of your robot. So this is going to be hanging from this bracket all the way here. So now if your rover is moving, or I just want to see the natural behavior. So this system has a mass, and I have assigned the appropriate materials and everything. So it has a mass, it has moment of inertia, it has its own stiffness matrix, everything it has. So now it's gonna have natural frequency. So it's gonna be, I think, root k by m, stiffness by mass would be the natural frequency. So the ratio is going to be stiffness by density. So we want to find what are the group of natural frequency this system naturally has, which we cannot change. We have to change only by changing the stiffness or changing materials. They do change, but overall the natural frequency we can get a mapping. So let's see this. So yeah, so let's see what are the, you can see the numbers right here. So from zero mode shape 1 to 7, it's pretty much nothing. It's all zero frequency. Like there's really nothing to do. Let's see what's mode 1 look like. What is something is, yeah, something, an internal part is shaking. Yeah, there must be an internal part hanging around. That's why it's doing, but it's nothing serious. So, but we have something 12. So from mode 8 to 12, we have something serious. So let's see what happens at 8. Each one we'll just go through. So that's why your design is very critical. I've seen what is 8, but you can see this is a spring element. You can see a spring element to hold the battery tight to this. But what happened because of the structure? Did you see here at 82 Hertz? This is going to happily start swinging. So is this a good design? Can we come up with a better design? Do you want to have the steel, like steel spring, like holding it tight? Yeah, not a great design. That's how we start saying, oh, okay, 82 Hertz. Our motor is gonna be, if it's gonna be at 100 Hertz, this problem is not gonna be there. But if it starts like 80 to 82 Hertz, this is gonna happen. And most probably the spring could come off or break down if it's constantly at 82 Hertz. So you should need to know what is the natural frequency of a system. So let's go to the other one, 9. So again, the mode 9, this time it's going to be in the sideways. Yeah. So again, so two frequencies, 82 and 108, we have this. So hopefully your system is not in that range. So mode 10, so this would be interesting. The mode 10 would be, so mode 10 is 156 Hertz. So let's say you designed a system where the actual vibration of the system is nowhere near like 108. So you just pushed it all the way 120 Hertz. No, push it even above 150. Now you have a different problem. This entire system would be vibrating. You can see how the brackets are changing. So this is how you see. When it says red, there's a maximum deformation, and maximum deformation happens at the bottom and also in the bracket. So you just see all the components that's being moving. It's pretty much everything is like the apple is shaking the tree. That's how. So definitely you don't want it to be at 156. And you can see what is the 11. 11 is 177. You can also see a 177.25. Let's see how it behaves. It's going in sideways now. So what's interesting and is that 177, the bracket, the top portion has nothing to do. It's pretty happily sitting. But your action camera, GoPro is going to move in left and right. So now we have to be, if you're going to be at 180 Hertz, this is going to happen. So that's how we would be saying. And let's say at last frequency, 223. So again, this is the same culprit again, this beam. Now each one is moving. So overall, like you just see, hey, this is what my frequency is going to look like and where is it. So each subsystem will have its own, based on the shape and the mass, it's going to have its own natural frequency. You start mapping it out, like, writing each one, what is the natural frequency. When you put everything together, they all behave completely different. In that way, you can predict. So if this part goes now to vibration testing, the shaker table I showed in the previous one, it would fail. If it's at 177, like yeah, this it's gonna fail. It would just mechanically break right here. If I just put it at 177 hertz for 10 minutes, this would just come off, because at resonance frequency it starts absorbing all the input energy. It will just come off. So that's how it is. Any questions here? Yeah. Anything you want to see?
Yeah, that's thank you. So I'm waiting
Yeah.
for others to ask questions. If not, I'll ask another question.
Yeah. Okay. Anyone else questions? Okay, then you can go ahead and ask. Yeah.
Yeah, that's true. So now we're gonna talk about like fatigue analysis. So which stage you have to consider the fatigue analysis here in Ansys?
So we have, so there are a bunch of models for fatigue. So what, so what
So
is
the
your
question,
question?
excuse
Yeah.
me, just the question is that you run fatigue analysis separately, just for fatigue. Is that correct?
Yeah, fatigue analysis
Okay.
separate. Yeah, yeah.
And you give it a certain number of cycles when you look at the failure, or you can count the life prediction. You can predict life when
Yes.
you use
So
Ansys. Okay,
so
yeah.
so yeah. So that is, yeah. Fatigue is like, the cyclic loading. So in the cyclic loading, yeah, we can do the life prediction based on which model we have. So we have several models like SN curves from Goodman, multi-axial failures, and what stresses to use. So so no fatigue model is perfect. So they keep coming up with new ones, and ANSYS is integrating, like with the lag of 4 or 5 years before they are keep integrating. But I can show you. So overall, like random vibration, yeah. So this is the random vibration you can see here. So I just ran some random vibration. So this is the power spectrum density. That is, so you just give like, it's like a probability, like, it's random. So anything it's random, like stochastic process, it would give a like a probability curve, like what is the power gonna be, like a power spectrum density. So I just gave like, say, 1 to 300. Let me give like 400, and the higher the number, the acceleration per hertz, like that means at that frequency the probability is higher to have 10G. So let's say I give like 100 or something. So this is the kind of profile. This is what they record, the like OEMs, big OEMs like Ford, Chrysler would record. They have a testing engineering team. They put accelerometers on the system, like on an engine or something. Like over here, they keep putting 6 accelerometers and test the data, and they give it as a power spectrum density, something curve like this. They said, hey, you guys take your subsystem, test it for this. If there's any failure, mechanical, electrical, let me know. So in a way, it is a fatigue. Indirectly, it comes down to fatigue when it's vibration. So this is one way of tackling. There are several ways, but this is a common way I use. So what I would say is, like, I just gave an input. So in the power spectrum density, it says which direction. This is the tabular data. So I'm just saying Y direction. Let me give it an X direction. You have to do an X, Y, Z. So let me give it an X direction, the sideways. I don't know what is going to happen. So let's run it. Solve. There's some error. Let me close this. Yeah, let me delete. It's taking longer than usual today. But yeah, the idea is like, once you give it the random vibration, it gives you what is the stress you would see in the part. If that stress is below your ultimate tensile strength, the material breakage point, yeah, you're good. But if it's very close to it, you want to, redesign it. So that's how we do the stuff. That's one way of approaching. They also have several fatigue models embedded, but I haven't explored them yet, but I can show this one. Yeah, so in the model, like once you can go from solution, you can right click, transfer data to new random vibration. So if you want to activate any random vibration, anything, ultimately it comes from model. So even if you directly go more without model analysis, nothing could be done because these natural frequencies are fed back to here. So they just do a mathematical computation to give the values. So everything starts with model, the natural frequency. So let's go to setup and do it again. So yeah, so we saw all the natural frequencies last time. It's all fed here. So we have the model analysis settings. Okay, now it says like, what do you want to do? PST acceleration velocity. We usually go for PST G acceleration in terms of G. So let's say what's the load data? Let's give it the load data. So at 1, we would say 1G, and next at 100 Hertz. Yeah, 100 Hertz, we would say 10G, and 300 Hertz, it's like 45G. So, they say, let's say someone gave this data, they are just riding on Mars or something, or in Arizona, they just predicted, hey, this is the kind of G you're gonna have. We predicted, we want your subsystems, all the subsystems going into our skeleton to withstand all this vibration load. So this is the power spectrum density graph, G square by Hertz. So, and now we have to say which direction. So we have X, Y, Z. So most times when you do it, we have to do triaxial vibration. That is Y, X, Z, all the 3 directions. We have to be testing it. So most probably the worst case would be the sideways. Sideways, they behave completely in a different way in each axis. So let's try it X axis and see. Boundary condition, fixed support. It says, where do you want me to apply? This is where I fixed it. So this is where we are going to be applying the load, the vibration load we specified here. And what is the direction you want to apply? So in a X direction. Yeah, so we are going to apply, hold this part in the red, whether it's fixed, and move it in X axis. Let's see what are the stress that it gives off. So it's a stress equivalent 1 mices. We also have a fatigue here. The fatigue tool. I haven't used it before, but yeah, you question the predicted life and everything would come. Life damage. So it is using Steinberg method, and stress over here is like equivalent 1 mices stress. So somebody would use principal stress, someone would use 1 mices shear stress. So it depends. So I don't know why it's right now. I will just delete them, come back and see. So let's just see the equivalent stress. And here in the equivalent stress, you can see it's 1 sigma. That is, what is the 1 sigma means, like, 68% of the time, what is the stress you're going to be seeing? And now let's say 2 sigma, 95% of the time, what is the stress you're going to see? 3 sigma, 99% of the time. So since this is being random, we have to go in terms of probability. Every time you see random, that means stochastic probability comes. So we'll start with 3 sigma, or we'll just see what each one says. So let's go and put 1 sigma. And let's see what is the stress we're going to see. Yeah, it's done. So at 1 sigma, we are going to be seeing 5057.4, that is 5 megapascal. Uh, so what is the material property? Let's see, mostly it's plastic. We will change the units to megapascal. Yeah, so now it's easier. So let's see, what's the plastic ABC? It's the tensile yield strength is like 36 megapascal. So now we know it should be within 36, or all the plastic is gonna break. And guess what? How much we have? We have, oh shit. We have 3,000, 32,000 megapascal. And where is it happening? That's gonna break. So yeah, this is not good for such a very high G. Let's see what the stress in one Mises stress is gonna look like. 2 sigma, 3 sigma, 99% of the time. Yeah, so 763 megapascal. So what it actually says is like, um, so this is the probability at certain probability at resonance frequency. So what is the probability like, at 153 hertz? It's going to have phase 10G or 100G. It's much less. So that's why that is the kind of thing. So 1 sigma is very highly, you don't want to go with 1 sigma because you get crazy. But you look at, uh, something like this. Even this is higher, 763 megapascal, 254. Okay, so 99% of the time you're going to see 763 megapascal. So that means my PST acceleration is too high. Let me bring it down to 10 and see how this is going to look like. Let's pass this time. Uh,
Aniroodh, this looks great, but
okay.
can you also do thermal?
Yeah, we can do thermal.
Thermal in terms of the, let's say, the structure, or can we say, because I think in Ice Pack, also within Ansys, you can do thermal on the PCB as you power it up. Let's say you have a high-end computing process. It would look at the thermal and it would generate the heat. As previously noted to the team, that you want to look at the heat and where it's generating to pick the material that either absorbs the heat or dissipates it.
So yeah, this is this is called steady state thermal and transient thermal we have. So yeah, you can do both the thermal and you can see what is the temperature profile and everything. And it's pretty quick. Thermal is quite straightforward, so it won't take a lot of computational time. So yeah, so I just fed the material. One good thing is once you set up all the material, you can just feed it through different suits you want. Let's say we just generate a mesh quickly. Yeah, so mesh is created. So now let's say we have high temperature. Let's say at this point, for whatever reason, there's super high temperature. Let's say, we'll put it, where do we want to put it? Okay, we'll say we have a high temperature, it's near engine or something, and the magnitude, let's say 125 C. So we have 125 C over here. And you don't want the cameras to have high heat. Let's see how the heat is propagating. So let's see, thermal gradient, that's temperature gradient, the temperature, how its profile is going on, and total heat flux. So let's just solve it and see how it's going to look like. So you would be seeing from here how the heat flows all the way down here, and you can see what temperature your camera systems would be. You can also find out what time it takes. Running during the solution. Okay. There are a lot of materials, so let's think. Yeah, these materials, yeah, but for some reason it's not running. I've run a bunch of them, but yeah, this is where we do it. Like you give the temperature right here and the temperature flows all the way down and you can see it's 125 C. By the time it comes, it'll be like 90 C. There'll be temperature loss. And we can also find out the transient, like how much time it takes from here to go. And you can find out by using transient. Yeah, transient thermal. So, okay, let me do it this way. It's not coming. Yeah, something the model I have to go back and clean it up and do something. It will take time. But yeah, so in transient thermal, we can do the same stuff. Let's see. So transient means with the time, the steady state shows the final, but you can clearly see it's so much time. Let's say it takes 10 minutes for the heat to transfer from the bracket to the camera. How much time does it take? So these kind of transient, we use quite sometimes transient in many of my application I use. So let's generate mesh. Insert. So you can have convection, radiation, heat flow, everything. So let's say we have a heat flow this time. Let's say we are just giving a heat flow of 100 watts. 100 watts heat is being given here. And then you can also use some convection. Insert convection, the camera surface. So let's say all these surfaces are gonna have face the convection, that is like any airflow around it. I'm just playing around. So let's just apply. So these are the surfaces where the air is going to flow and heat loss could be accelerated by convection. So here, interesting thing I like to show is so here info time dependent. Okay, there is a way to bring it from Ansys. You can bring certain film coefficient because the H heat transfer convection coefficient, like we generally just put a constant number here. Just say constant like 10, 5 to 15. But there's a beautiful graph with different temperature you can put it. And I forgot how I did it. So Ansys has it. So in that way, it'd be more accurate and it's very critical for us. For right now, we can just put 10 and most probably it'll have the same error. But what to look for? Thermal gradient, anytime temperature you want to see what's the thermal distribution. total heat flux, how the heat is moving around. What else we have? Probe, radiation. I think that's enough. Directional heat flux. Yeah, this should be good. Let's solve this. There could be the same and some pivot warnings would be coming. Yeah, it could happen many times. We have so many matrix and each surface is interacting so many ways. There could be some error happening. We have to go and find each surface and solve it. If it's just two bodies, it will be pretty easy. Let's see. Oh, it came. Okay, that's surprising. It came. So yeah, you can see the temperature. Right now we are just giving 100 and none of them are really passed through down. So that's interesting. I thought it will come all the way. So you can see the ambient is 22. Everything is ambient. So if you give 100 watts of heat, all the heat is right here. It's not even going down. And the most it goes down is here a little bit and then it cools. So let's say because of convection, yeah. Now let's just freeze the convection and let's suppress it and run it. This would be interesting to see without convection if the heat is flowing much faster. I don't think convection matters because, you know, below the battery, it never even went. So heat is not high enough to penetrate it. The enclosure itself sucks it up. Ah, model has no convection variation. Okay. So yeah, it doesn't matter. So no matter how much 100 watts is not high enough. Let's say we give a temperature of here, apply, and give a temperature of let's say 150 degrees Celsius. Very high temperature, and let's just run it. And does it make any better, or this bracket itself is thick enough that it sucks up all the heat and everything? Let's see. I want to show beautifully how the heat flows from top to bottom. Looks like, you know, the bracket is strong enough. Ah, yeah. No matter what you do, its heat is not flowing below it. So let's see. This is how the heat is building up and then it saturates. So let's see what the average, minimum, not much difference. Let's say we apply the temperature right at the center. Let's say right here. So we just remove from the top. Let's see how heat is flowing. So somebody just applies 150 C temperature here. Is the heat gonna flow up? I still see like heat gets localized here. It's not gonna flow up or down. So one good way to see is like you have very high heat or some heat exposure happened or something, your camera is good. all the battery and everything is good. That's the job of a battery enclosure, right? Like very high heat or burst, shock, you drop it, your battery should not be damaged. So it's doing a pretty good job of this. Let's see in this bracket, the holding bracket, what happens. Temperature. Yeah, you can see there is some heat flow, but nothing sideways. So it just heat flows all the way down here. So at 150, the least is you can see at 78. So at the bottom, it's like 78 here. This is a typical heat flow. So this is how like you can define your system more accurate. You can just endlessly, permutation combination play around it. But yeah, take the system. They have the settings and everything very user defined. So you can choose at which way you want to apply the temperature and see how the heat is flowing through it. Um, any questions or anything you want to see here? Let's see what's the heat flux. Temperature flows. So this you can see how the temperature flows, and it's very highly localized. It's just following through the thickness. It's not going anywhere else. Um, let's see what happens now. Um, the bracket is heated up. Somebody has put a welding gun over here and just gets heated up. So does it really spread the heat throughout? So any kind of damage happens across the system, you just want that part to fail, not to, just spoil each one, like infect each one of them. So in that way, like so far we saw each bracket is just handling it itself, not transferring the heat or stress outside. So let's see how the entire part is under heat, what happens. At any time, you don't want your battery to get heated up, like, Samsung Galaxy heats up. So far it's good. Heat is not being spread to the. Yeah. So now heat is spreading a little bit. So it's so slow, it's taking time to see. So the animation is not in, but you can still see the most of the bracket. Like if the entire part is heated up, it's all red, you can see. Now the heat is being transferred slowly to the servo motor. The motor gets heated up, not great. And the battery enclosure gets heated up, but still not the battery. Battery is still protected. Yeah, battery is getting heated up right here. And you can take a probe and check what is the temperature. It's all 150 and it's 98. So it's 61, 75. And right here it is 35, 34. It's not bad. 35, 34 it can handle. If it's above 50, it's an issue. So yeah, what's the servo motor? So usually I take a probe and look at the parts of affected. So you can see 92, 73. So yeah, servo motor would be affected because it's directly bolted to the bracket. So that's the idea. So yeah, the mostly like we just see how the thermal gradient, the temperature spread out, scattered along the profile and see. And whatever the condition you are, like you can specify the load. I just randomly played around to show how it can spread out took so much time to find, how to way to spread it out. So yeah, this is one way of looking, and you can get thermal stresses and everything. And if the stress is very high with thermal fatigue, like thermal cycling, it will fail. So these are some of the, a lot of analysis we'll do upfront to make sure what are the failure criteria as we know.
So,
Any
and
question?
with the rest of the students, I want to let them know, and some advice they couldn't attend, so they will be watching this. Ansys has sponsored us and is providing support to the Michigan FC nonprofit organization for the student simulation. They provided a license of each of their package. So one, we're thankful for your support, Aniroodh, and then two, for their support and partnership with the community to support the students. So I know a lot of students are, or some of the students are looking at this and like, well, okay, this is great, but do I have access to it? And Ansys will provide the access to it. So Aniroodh, if you see the ice pack below, just a little bit going down, right?
Yeah, here, yeah.
So to the rest of the team, this ice pack, everything is done in a simulation environment. We no longer build stuff and then do analysis on it. You want to do a lot of analysis upfront, simulation, and as you simulate, you go up, you move forward. I think last week I went over a camera design internal into the circuit board and everything. So this ice pack, I would utilize this package to run the simulation on the PCB, printed circuit board, where all the electronic components are. I would run this and it would tell me how hot my board is getting once I supply power to it. Knowing which component is hot, I would either have a fan there or heat sink or pick the right material for it, just to give the other team members a perspective. So I want, I think, Aniroodh, I'm not sure if you're familiar with the FPD Link camera systems that's made by Texas Instrument coaxial power. And I reviewed a whole camera design.
Yeah.
Exactly. Yeah.
Yeah. So this is a better picture, like the Ansys Ice Pack. That's pretty good tool for all the electronic packaging. That what you saw is a mechanical design, like all the bracket. So now what happens inside the camera? So inside the camera, you have a bunch of chips. They also produce heat. So you need to have heat sinks. So this is a heat sink. So yeah, you can see all the heat sinks and everything, very simplified. The chips would produce the heat. So we have to do a heat mapping. So everything we start map. This is a classic heat mapping. So you can see what is the motherboard, plus the heat sink and everything. So the idea of the heat sink, as you see, yellow is red is hot and green is like cool. So the chips would produce extraordinary heat. So that's why on top of the chip, we put a sink. Immediately want to dissipate the heat because heat builds up, it's done. So you can see right here, it's all red. I would put a sink, move the sink and put it here, or put another sink to solve the heat crisis there. So, and you can see how the heat is being spread out, red, yellow, green. From 105, it's like, say it's 80 and this is 40. That's how it splits it out. So this is a whole another topic. Maybe I can take an example next time and show you how, inside we can do it. And so yeah, this is like strategy. So you cannot have all your laptops, phones, everything gets heated up. So how good are you going to dissipate heat? And the internal temperature of this enclosure should be much low. Say the target is less than 50 degrees Celsius. If it's above 50, 60, 70 or something, it's okay, but the life would be reduced. So if it's less than 50, you have amazing thermal management system. Your life of the product will be like 20 years. But if it goes above 50, like 60 or 75, you say the reliability comes down from 20 years, it will be just like 10 years or 12 years. It won't fail overnight, but overall everything gets heated up, fatigue happens. It's when you switch on and off, fatigue keeps happening and goes off. So that is the kind of thing Ansys iSpec does. This cannot be done manually or hand calculation is impossible. Such a complex like 3D. So and testing forever, it's really very difficult. So best tool is analysis. And Ansys did a great job. maybe sometime I can walk through it. But yeah, it's good for people who are watching this who would like to learn about this too. So Ansys is great, a lot of flexibility, and made a simulation taken to even to, for all the common people. So yeah, that's it. That what we discussed is inside this camera. So now I went outside the camera, but even inside there's a lot of details in it.
Yeah, great. Yeah, this is very, as an electrical engineer, this is very informative and educational for me.
Okay.
So I'd just like to go through the team members of what Aniroodh explained today. If you have seen it before, if you've done it, or where you think you can use it in applications, just random ideas. There's no such thing as bad ideas, but I'll leave it with the rest of the team to give their perspective.
Yeah. So in my university, we had a project where we built a rover for my engineering class, and I feel like if I use this application, this kind of Ansys program, it would have helped me determine, the pressure points, the heat flow, all that kind of stuff. So I find it really informative, and I'd probably consider using that next time for sure.
Awesome. Yeah.
And yeah, for me, I used this software once back in November with my project was a CFD project. My professor just gave us like a random part with 3 inlets and 1 outlet, and we had to do different simulations where the 3 inlets had different temperatures going in, and we want to see just how it would look like, and then also show the temperature going out. And for my senior design project right now, it's a sleeve that measures the angle of a person's arm. We're using it to target stroke patients because sometimes they contract their arm without them noticing. So we're making a sleeve that detects if their arm is at like a 90-degree angle for some certain amount of time, then it like alarms them when it does happen. And obviously, like, it's not very fancy, but if we were to make like a more fancy one where the software was embedded in the sleeve or whatnot, we can I could probably use this to see how like the heat in the sleeve itself, to see if it's like too hot for the patient and stuff like that.
Yeah, that's interesting. Yeah. So yeah, you can describe the model, and yeah, there are 2 steps. First is describing the model and seeing it, and next there's one more step of optimization, which Ansys is working. They're doing pretty good. But before we used to do it manually or write some script, that will be very intense. But yeah, first understanding the model itself, Ansys does phenomenally great. Yep. Any other thoughts or something? Next time we could gather on any other topic. Something.
Yeah, this is great presentation, Aniroodh. I like it. As an electrical engineer, I have appreciation for mechanical stuff because wires and contact system cannot operate in free space, right? In the real world, and everything has a vibration profile to it. So this is great. This is great. I mean, we're continuing on forward until we get approval from the facility that we will meet on site. So thanks a lot to Mo. Last week he talked about the CAN protocol. We have ordered 10 devices for the students. They will have their 10 or so. I will get the part numbers from him. And we should be able to go through a couple of projects a week, if not 1 project a week, to go through the CAN protocol individually, mechanically, electrically, system level. That way the team has a good background and can put that on their resume, as something they worked on and can speak to it in an interview. And also it's educational, like whether you're doing a different protocol, but if you have a good understanding for one protocol, you can use it somewhere else, whether it's a higher speed, but you have the fundamental. Okay. So in moving forward, we will have access, I know, Aniroodh, you heard the word access, meaning you gain access to the building, but it's actually a local nonprofit that we're working with to utilize their facility and support. So we have access to their facility, about 20 or so chairs with a projector and everything, and they will be supporting with some of the computer accessories and some of the test devices also. So, and moving forward, just let the whole team know that we're going through some of the basics, different systems. Mauricio went over high voltage. I went over a camera system, high speed, design of the PCB, the data rate, the frequency. Mohammed or Mo last week reviewed the protocol in terms of the data transfer from one device to another. This week we're reviewing vibration, thermal, and other analysis. Next week we'll review another project which is a little bit different than this. And then hopefully by the end of these presentations, when you get to do a project, you have all this background and understanding. You're not going to design something and build it without doing all the analysis, whether it's electrical or mechanical. And Aniroodh can attest to the way that I bring people into the company. I don't give them a project. I take them through a training. And Aniroodh, you can speak on that. So that's the methodology that I told the rest of the team, is giving somebody a project on week one or day one or first month in my view, is not a good idea. But giving them some background and understanding and different ideas, what has happened in the past, what you can improve. That's, if you want to speak on to that in terms of your experience, how that has helped you.
So yeah, I can. So for the people who are viewing, a lot of students or engineers, just Ansys is a great place. So you can actually, you just get fascinated. Don't be obsessed like, oh, I should fix this. Just take some camera system. There's a lot of CAD models in online or your own system. You can do it quickly. You just saw me. I was just playing around it. Like, I just put some presentation and then open session. You guys asked something was going on. So just play around it and start asking why. Why is this happening? What is? And from you go reverse engineer and go back to your textbook. So many times reading textbooks and coming here would be like, what's happening? It's not visual. This is more interactive, and you will have more hands-on experience practically. Instead of putting thermocouple and measuring, you can't see this visually. All this thermal gradient you cannot see in real life until you have a thermal image camera. That's expensive, but here you can do everything. So I'd say just Ansys has endless suits. They have so many suits, literally like 50 PhDs gathered here. So just pull them, each one of them, like magnostatic, IC engine, whichever you want to learn, like fluid flow or how the blood flows inside heart valve. Download a model, put it inside and see. There's a lot of YouTube videos and everything. So just be fascinated by how beautiful the mechanical systems are. And this could not be done 20, 30 years ago. We are fortunate it's happening now. So be fascinated, and learning will be automatic. It not be hard. So yeah, and then you start loving what you do, and there won't be any stress. If not, you feel, oh, I'm stressed out to do this. No, just get fascinated with the work. That's what I would say. Yeah.
Yep. And we do have a network of support. I mean, I don't want to say open the network line and reach out to Aniroodh 10 hours a week, but there's literally about 15 to 20 engineers from hardware to software that are going to support the team. They're not meant to solve problems, but they're meant to remove roadblocks. Or if you come up on something and you spend a couple of hours trying to resolve it and you think you came to a dead end, okay, great. That's when you reach out, but maybe not the first 10 or 15 minutes.
Yeah, please, just be bold and go around and ask questions. Don't be afraid. Until you ask, how will you know? So even I don't know many things. Many times I interact with people. I just learn every time new. Even now, something I learned. So just keep learning and ask be asking questions. And more learned I learned is with the interaction and discussions, and just open mind, keep an open mind, not like I've done so much of this. Every time I think I've finished it, something new even keeps coming. But I just keep fascinated, not get stuck anywhere. So feel free to reach out if any roadblock or need help. Yeah, I can. Abbas, I know very well, so definitely I can help. So yeah.
Great, thanks a lot, Aniroodh. Any other questions or feedback or how we can support you better? I know we're not in a setting we can take on the software, but I'm setting up the server that you can log into the server remotely and access the software. That way it's not on a person's, on one of the students' specific laptop, or, oh, I need to gain access to it, where it's on remote server and you can tap into that and access it easily. And the Altium is to design the printed circuit board. We have access to that through Altium First Competition Robotics team, and then Ansys through their support and sponsorship of the students locally here in Metro Detroit and other packages. So once that's done, hopefully in the next 2 to 3 weeks, I will have that. I will give you the remote access to it, and then you can access it and run simulation, because one, you don't want it only on your laptop and somebody else wants to access it. And two, you don't want to have to go to the facility to access it, where we work and live in a virtual world now, that it should be done as such, and I'm working towards that. Any feedback or ways to improve or help you, or what you gained today out of the uh, lecture or training or examples?
Yeah, so I really enjoy the visuals. I'm really good, like I'm more of a visual learner, I'll be honest. I learn when I see stuff, being done. So I really do appreciate the Ansys program and how you showed everything, and you kind of gave us like, different examples and different procedures and stuff. Yeah, I really appreciate that. It was really helpful.
Yeah, thanks, Mushidaba. Yeah, like it's more easy to show around than putting in PowerPoints. It takes so much time putting all the
Yeah,
videos
exactly.
saving. Yeah,
Yeah.
it's very interactive to show around, and like because I don't know what people, so I just made it simple. Okay,
Mhm,
if somebody wants to go somewhere, then let's see. Yeah.
Thank you.
Yeah, it was great. I like the way that you presented all, the way that you did the solution and the presentation was great. Great experience. Thank you.
Yeah. Thanks, Gasan. Yeah, I will. The fatigue, I think you asked about it. Yeah, there's so much fatigue over here. In random vibration, I could have showed it better, but I think I just gave some number. It came big. But yeah, there is a lot of fatigue models. One is in random vibration. You can see.
Yeah.
Remaining, I myself haven't explored yet, so I should be honest
Yeah,
there. Yeah.
there is a question that can come up actually. Usually, if you can do fatigue for the whole assembly, or you start doing the analysis separately for each single part, that's another way to look at it.
So
So
yeah, the random vibration. One thing I would say, so yeah, this is the random vibration. So this highly depends on how you fix the part. So right now, this is the fixed support. Let's say I fixed this one. Let's say I fix these two. Fix it from here. It doesn't make sense why I do it. But if I do this, all the response would change now. So as you asked, like, which part, is it a system or an individual? Yes, individually they will be different. Like two of them individually will be completely different. But if you attach them, they'll behave different. And how you mounting determines the natural behavior. So every time you mount at different places, they're going to behave differently.
yeah, that it
So
changes the stiffness
yes,
of the whole system.
yes.
That's
So
where you get
now,
different response.
yeah. So that's the thing, and so that's why if it's a simple beam, you can do it. such a complex, like let's say at 9 or something, 10. Did you see it's completely now? This is changing, and the way you're mounting is different. So it's still 12. So now if you see, since I pushed at the center, all the frequencies will change at 199, 223. They all are pushed around. So yeah, how you mount it is completely different. So it's so non-linear, so many factors that you can't do it in an Excel or it's not a simple beam like 2D. It's very 3D and a lot of stuff. So yeah, you can get very explorative, but you'll get a feeling about it, and you'll learn a lot of mechanical concepts in a reverse way, more interactively. And a lot of stuff you can Google and read around, and they keep writing papers. I would say read Google Scholars more and more about this, and you'll get a lot of stuff. That's how I learned. So
Yeah,
yeah,
that's true.
yeah,
And we also have access to the Ansys Learning Hub through the sponsorship that Ansys has provided to the students and to the nonprofit organization to support the local community. So that's a big plus.
yeah. That's
Normally,
amazing. Yeah. Mhm.
yeah.
They teach both the theory behind it, all the partially differential equations, matrices, and also examples I've seen. But you can start with the interactive examples, and then you can, if you're interested to see, after some time you will be interested. What are the equations? Because endlessly you'll try to solve something. Then you can go back and see. But yeah, it's all recorded videos to and fro. You can start and stop when you want. But yeah, it's a great place to learn.
Yeah, this is a great point you make, Aniroodh. So a lot of students learning by the textbook, and they're like, okay, what's in it from? How am I going to apply this? Now you can take a differential equation, apply it to a system, and you can see the benefit of learning that in the math class. Differential
Yeah.
equation,
Some of
calculus.
the reason like people just pushed away from like CFT or a lot of Navier-Stokes matrix equations. Even here, there's crazy equations involved behind the scene. If I show, people have run away. So don't start there. Go from the other side. See more visual interactively. Build it with your hands. Then you see results happening, and then you try to solve something like say stiffness. Stiffness matrix is a very complex thing. Oh, how do I increase the stiffness? I'm trying to solve. Then you go back and read. Then you know what to look for. That will drive your interest to read. Then you say, hey, stiffness matrix depends on material, the design, what kind of curvatures you have. Why is it? Then you see a differential equation like dy by dx, the curvature. Okay, it makes sense. So you learn that way. You don't have to, gather everything in your brain and don't know where to use it. So that's how I learned. So I don't know complete picture, bits and pieces. I know where to look for things. In that way, I know some mathematics around it. If not, I wouldn't know everything. If I would have started, I would have never came here. So go start from here and climb up backwards. Yeah.
Sounds good. Thanks a lot, Aniroodh. And we're very appreciative and happy to have you present to our students, our community, and the knowledge goes on, right?
Yeah, it's endless. It's not. This is just a drop of an ocean. It's endless. And as we go, if any of you have interesting topics, yeah, let Abbas know. He will let me know. We can present
Yes,
something new. Yeah, sure.
for sure. You'll be invited, for future projects that we're working on. I
Mhm.
think, or possibly present another topic. But the way I see it is the other presenters, they will be part of the team one week at a time, where they look at the project and they give some input, and maybe 2 hours or so of analysis project, and going through it, like designing something from scratch. We're gonna have a project from scratch, and we're gonna define it and then start designing on it, and that's when we're gonna probably reach out.
Okay, sounds good.
Sounds good. Thank you, everybody. Well, Anwar, thanks again, and
Thank
have
you,
a
guys.
good weekend, and enjoy it. Be healthy and safe.
Yeah.
Thank you so
Okay.
much.
Thank you.
Have a good weekend,
Thank
everybody.
you.
Yeah,
You too.
take care.
Bye
Bye
bye.
bye.